Hey guys, this video is to explain section 9J. It's on pages 29 to 32 in the notes, and it's all about conditional probability. So the idea in situations that involve a sequence of events, when the outcomes of the second event depends on the outcome of the first, we'll then end up finding the conditional probability that event A happens knowing that event B has occurred. So we call this the conditional probability of A given B, and we have some notation for this. So the P parentheses notation, A, a vertical bar, and a B, here's how this works. B is considered the given event, and A is the probability of the event you're looking for. So if we develop a formula for this, I'm not going to put down any formal proof. I'll just get my marker out here. If I tell you event B has occurred, that means I say forget about the whole sample space, only look here. So if I told you to only look here, and then I asked you, well, what's the probability of A happening given that B happened, it should make sense that you could tell me, well, if B happened, the total, right, the idea of probability as favorable outcomes divided by total, you can say, well, if B has happened, the total of those outcomes, meaning the total in those regions, would be B plus C. And then of those, where has A happened, it's only B. So guys, the place where B is the region where A intersects B, and B plus C is region B, so we have this conditional probability formula. Okay? So that conditional probability formula, if rewritten, turns into something called the multiplication rule for dependent events. Meaning if you look at this and you say, what would happen if I took this expression and times both sides by the probability of B? Well, then I could figure out that the probability of A intersection B would equal this conditional probability of A given B multiplied by the probability of B. Or if I switch the letters around, the probability of A intersection B can be the probability of B given A times the probability of A. So intuitively, we've already used this rule on the tree diagrams where we said we were going to do some sampling without replacement. When we did sampling without replacement, we put the probabilities on the branches, assuming the previous branches already happened. So how am I going to know to recognize a conditional probability question? Look out for the phrase given that or the words if then, because if then, remember, it was called a conditional implication. So if you see if then or given that, it's a hint that you're solving a conditional probability problem. Okay, so here's the model problems. Model problems. In these model problems also, when I read them, I'm going to want to decide maybe some things that I've learned earlier in the chapter are going to help me solve them. For example, tree diagrams, Venn diagrams, etc. So if I have a group of 40 boys, 23 with dark hair, 18 brown eyes, 26 with dark hair, brown eyes, or both, well, that sounds like I should summarize this in a Venn diagram. So I'm going to do the usual. Before I even look at the questions, I have a universe of 40. I have a set of boys with dark hair, that's D23. And then I have a set of boys with brown eyes, so that's B18. And then here's where I have to make sure I've learned prior information. If 26 have dark hair, brown eyes, or both, that means the total of these three regions would be 26. So one of the things that we've done in the past is we've taken the middle and put an x in it, 23 minus x, and then over here 18 minus x. So if 26 people have dark hair, brown eyes, or both, then I could write the equation where those three regions sum to 26 and then solve for x. All right, so that'll be 41 minus x equals 26, so x is 15. That allows me to finish filling out the Venn with 15 here, 8 here, 3 here, and if there's 26 in total in those 3 areas, 14 people would be out here in the universe. Okay, now I can answer the probability questions. Dark hair and brown eyes. So that's the D intersection B area. That's 15 out of 40. Neither dark nor brown. So it's I don't have dark and I don't have brown. That's the outer region. 14 out of 40. Part C. Dark hair but not brown eyes. So we're in the D, we're not in the B. That's 8 out of 40. Brown eyes given dark hair. So this is the new stuff. Brown eyes given dark hair. B given D. All right, so I can follow a formula or I can just intuitively go through this. If I have a dark-haired person, I'm being told only to look in here. Let's color it in green. So if I'm being told only to look in here, then I'm looking at just 23 people, and of those, 15 have brown eyes. So I get to put 15 out of 23. Okay, so the denominator is not 40 because of the conditional probability idea. Next page. 400 families are surveyed. It's found 90% have a TV and 60 had a computer. Every family had at least one item. Of those families randomly selected, it's found that they have a computer. Find the probability they also have a TV. All right, so to me this sounds like I should work with a Venn diagram first. So I'm going to draw a Venn of 400 families. Okay, 90% have a TV, so that's T360, because 90% of 400 is 360. 60% have a computer, so that's C240, because that's 60% of 400. And every family had at least one. All right, so that means zeros out here. So let's solve for the regions here. 360 minus x. 240 minus x. Do a little bit of algebra. 360 minus x plus 240 minus x. That all has to add up to 400. So this is 600 minus x equals 400. So x is 200. So let's put those in. That's if x is 200, that makes this 160, and that makes this 40. Okay, so our Venn breaks down the regions into counts, and now let's find the question. We select a family at random, we find the family has a computer, so that's the given information. Find the probability it also has a TV set. Okay, so that means given they have a computer, only look in here. Of those, who also has a TV is what we're finding. So only looking at the region that has 240 people in it, and of those, 200 also have a TV. Okay, next problem. Now we have an urn with 2 red and 3 blue, urn B with 4 red, 1 blue. Peter's going to select an urn by tossing a coin and then taking a marble. So toss a coin, then take a marble. That sounds like a sequence of events where a tree diagram would be handy. Toss a coin. Once I toss the coin, I'll have a 50-50 chance of picking A or B as my urn. Once I pick an urn, I pick a marble. So the marble is going to be red or blue. Red or blue. In urn A, there's 2 red, 3 blue. So this is 2/5, 3/5. In urn B, there's 4 red, 1 blue. So this is 4/5, 1/5. All right, so then that means the outcomes are urn A, red marble, urn A, blue marble, urn B, red marble, urn B, blue marble. And then the probabilities are just found by multiplying. So I'll just quickly do that in my head. That's 2/10, 3/10, 4/10 and 1/10. If everything's right, remember previous concepts from the chapter, if I did this correctly, these probabilities, 2, 5, 9, 10 out of 10, should add up to 1 where something went wrong. Okay, now I'll look at the question. So the question, part A, determine the probability that the marble I end up with is red. So all I have to do is add up the branches where I found a red one. So that would be the 2/10 plus the 4/10. So we can get 6/10 for that. Question B, given that the marble is red, what's the chance that it came from urn B, given that it's red? Okay, so we just found that there's a total of 6/10 that are red, and of those, which one came out of urn B? The 4/10. Okay, that's a simple fraction because those 10s will cancel out, leaving me 4/6. Remember, guys, you can leave these fractions unreduced, or you can reduce them or get a 3 sig fig decimal. Okay, next problem. On any given day, machine A has a 10% chance of malfunctioning, and machine B has a 7% chance of doing the same. Given that at least one malfunctioned today, what's the chance that it was machine B? All right, so here again, I feel like I'm doing a sequence of 2 machines. So first, it's machine A, so it either works or malfunctions. So I'll just use A and A prime for A works and A malfunctions. Let me erase this A that I wrote there. And then I'm going to go over to machine B. And machine B is going to work or malfunction. So we'll use the prime symbol for the malfunction. So this makes sense, I think. Machine A has a 10% chance of malfunctioning. Machine B's got a 7% chance. Okay, now I can fill in the remaining probabilities just from a complement rule. And now my tree is done. Given that at least one of the machines malfunctioned today, what's the chance that it was machine B? Okay, so let's write out the outcomes. AB would be both worked. AB prime would be A works, B doesn't. A prime B, A doesn't work, B does. A prime B prime. And then if we multiply our branches here, we have 0.837, 0.063, 0.093, and 0.007. All right, so let's think about this. Let's check this off. We're looking for, given that at least one machine malfunctions today, at least one malfunctions, what's the chance that it was machine B? So let's look at numerator and denominator. At least one machine malfunctions is the favorable outcomes for the denominator. At least one malfunctions would be any of these 3. So the sum of those probabilities makes the denominator. And then what's the chance it was machine B that malfunctioned? So then I would need, of those 3 things, these 2 had machine B malfunctioning. So you'll notice that I'm not really using those fancy formulas from the parts of the notes at the top of page 27. Really kind of intuitively figuring this out through a culmination of all the probability rules up through the chapter with the idea of what the heck now is this conditional probability idea? How do I form the numerator and denominator based on the question asked? Okay, so then if you simplify that, you can simplify all this to 0.429 as a 3 sig fig decimal. Turn the page, there's 2 more examples. Okay, so the 2 more examples. The probability that a randomly selected person tests has cancer is 0.07. The probability he or she reacts positively to a test, which detects this cancer as 0.95 if she has it, and 0.03 if she doesn't. Determine the probability a randomly tested person reacts positively. Okay, so again, you have to get used to the idea that this information can be organized nicely in a tree. So first, I have to write down either a person has the cancer or doesn't, and then when they take a test, it either comes out positive or it doesn't. So there's only a 0.02 chance of having that cancer. And then if you have having the cancer, I put that on the wrong branch, 0.02. If you have that cancer, 95% of the time you're going to react positively, so the test detects it 95% of the time, and 0.03 if she doesn't. Okay, so still for these 98% of people who don't have the cancer, there's still a small chance that they react positive. So that's that information summarized. And then, these three numbers, the 0.98, the 0.05, and the 0.97, we add to the tree from the complement rule. Okay, so the outcomes then are cancer, test positive, cancer, don't test positive. Don't have cancer, test positive, don't have cancer, don't test positive. The probabilities of these outcomes are just multiplying the branches together. So I've done that. That's 0.019, 0.001, 0.0294, and 0.9506. Okay, so then the questions. Part A, what's the chance someone comes up positive? So I'd go to the branches where a positive result happened, and I add. So that's 0.019 plus 0.0294. Adding those, we get 0.0484. Part B, has cancer, given I react positive. Has cancer, given a positive result. Okay, so the 0.0484 was the total proportion of positive results, and then the have cancer would only be the 0.019 of those. So that's 0.393. Let's take a pause on this 0.393. It shows you the idea of when tests are given, even though it sounds highly accurate, 95% chance it tests positive for someone who has it, and a pretty low chance, 0.03 of that false negative. But in general, when you put this together, holy cow, given that the test is positive, there's less than a 40% chance the person has cancer. So guys, in real life, these probabilities of positive, they need to be much higher than 95%. Can't afford to mistake this 5% of the time. And the 0.03, that's also pretty high. So you can see with that, even though it sounds like it's a pretty good test, it's not. So those results put together say, if someone tests positive, there's still only a 40% chance of having that cancer. That means people really need to work harder in the laboratory coming up with a test that's more accurate. Okay, next we got a team of judo players. 13 have won a match by throwing, 12 have won by hold down, 13 have won by a points decision, etc., etc. Okay, I'm hearing a 3-circle Venn diagram for this team of judo players. 3 circles for the team. Let's start filling it in. The universe is 30 people. 13 have won a match by throwing, so that's T13. 12 have won with a hold down, so that's H12. 13 have won with a points decision, so that's P13. 2 have won by all 3 methods. 5 have won by throwing and hold down. So guys, the throwing and hold down, if it's 5 total, this is a subtraction needed because we don't have the word only. It didn't say 5 won by throwing and hold down only. It says 5 won by throwing and hold down. So that means this throwing and hold down region over here can only total to 5 people. So I did need subtraction. 4 if one matches by hold down and points. So that puts 2 over here by subtraction. Let's make that 2 with a pen. 3 have 1 by throwing and points. So that puts a 1 there. Okay, and then let's fill in the remaining regions. If T has 13, I'm counting 6 so far. That puts 7 there. If the H region's supposed to have 12, I have 7 so far. That's 5 there. If the P region's supposed to have 13, I have 5 so far, so that's 8. Let's count these 7 regions. 16, 19, 21, 23, 28. That means there must be 2 people who won by none of these 3 methods. Okay, so that's part A. I put all the information in an appropriate Venn diagram. So now in part B, if I go to find these probabilities, remember all of this notation you should be comfortable with. We've done this not only in the Venn diagram chapter, but now also in this chapter with the P parentheses notation. Okay, so B1, let's get the probability of T intersection H. I see 5 total in there. B2, let's get the probability of P. I see 13 out of 30 there. B3, the probability of H given P. So given P, I'm only told to look at 13, and H has 4 out of those 13. Part 4, T union P. So if I do T union P, that's going to count. Let's get my eraser here and erase the shading. Can I do that? That's kind of annoying. T union P. All of this would be T union P, these 2 circles. So there's 6 numbers to add up for the numerator. 7, 10, 13, 15, 23. Add to the 30 in the universe. Part 5. T given H prime. All right, so if I'm not in H, let's get like a black pen. If I'm not in H, then I'd be one of these guys. These guys are not in H. So that's the denominator. 7, 8, 16, 18. Of those, how many were in T? 8 of them. Okay, and then the final part 6 right here, I'll squeeze up here. T intersection P given H. So if I'm given in the H, then I'm only told to look at 12 people. And the T intersection P part of that is only 2 people. Okay, so that was the hardest problem because of the 3 circles and notation, just getting used to that. That ends section 9J.